ocean movements in general. So ocean movements that occur in oceans are categorized as waves. Maybe I'll try and point you some important terms. Waves, so waves, tides, and currents. So we're going to talk about today. So waves are formed because of friction between wind and surface water layer. And the stronger the wind is, the bigger the wave is. But they die out quickly, reaching the shore or shallow waters, so they don't last long. Then there are tsunamis or tides that are tidal waves. They have large wavelengths and greater intensity and very, very destructive power. Tsunamis are caused by displacement of large masses of water. So earthquakes, volcanic eruptions, underwater explosions like detonations of underwater nuclear devices, and landslides can potentially generate tsunami. And then we have currents. Maybe first I'll show you how the waves are formed in general, in contrast. Okay, so this was forming of the waves, and then we have currents, and currents are much like rivers, like river flows in the ocean. So there is a regular, constant volume of water that has a certain path, that has certain direction. These are cohesive streams that are currents. We can have horizontal or vertical currents, but we'll come to that in a minute. So what's going on inside the ocean? Even though it might seem steady, well, there are waves, there are tsunamis from time to time, but oceans are not a monotonous like bowl of soup. This image here represents the whole system of currents during, this is the whole planet, but this is during northern hemisphere winter. And blue are cold currents. Cold currents mean that they are colder than the flow is colder than surrounding water. And red are warm currents, which means that, of course, the flow is warmer than the surrounding waters. They all have different speeds, but the thing is that the whole system is rather stable. Currents are, or should be, rather unvariable. And they should remain in balance because a lot depends on this balance, but we'll see this later. And this balance is endangered by climate change. And currents, ocean currents, account for about 40% of global heat transport. And generally, they move slower than winds because winds are movements of air, and they, of course, move much faster. So horizontal currents rise mainly due to friction between wind and water, a little bit like waves. And also rotation of Earth, Coriolis force, and differences in water gradient also play a major role. And generally, vertical currents arise because of density differences caused by temperature and salinity changes. Because body of water is not a one layer. It's made up of many layers determined by water temperature. There's a top surface layer called epipelagic zone, and it's sometimes referred to as ocean skin or sunlight zone, because in this layer interacts with wind and waves, and this mixes the water and distributes the warmth. So it's a warm layer. And at the base of this layer, there is so-called thermocline. Thermocline is a transition layer between warmer mixed water and cooler water below. When you swim in the ocean or in the sea, it is relatively easy to tell when you have reached the thermocline in a body of water, because there is a sudden change in temperature. Suddenly water becomes much, much colder. In the thermocline, and the temperature, here you see the temperature, it decreases rapidly from the mixed layer to much colder water here. And in the ocean, the depth and the strength of thermocline can vary from season to season and from year to year. For example, in the tropical area, it is semi-permanent. It is almost permanent, and in temperate regions, for example, it is variable. It is deepest during the summer, and in the polar regions, it is shallow, or even not existent. The water column is cold from the surface to the bottom, and there is a lot of mixing in the polar regions, which also has its consequences. So, ocean currents are complex and complicated by the fact that the Earth rotates from west to east around its axis. This is where the axis of Earth is. On the left, we can see a simplified image. What it would be like if the Earth was steady. On the right, when we add the rotation, land masses, unequal heating and cooling. And this complicates the system. It's not just the surface flow from cold to hot, but the whole system gets more complicated. Covering about 71% of the Earth and absorbing about twice as much of sun radiation as the atmosphere, the oceans are a major component of the climate system. So, like I said, about 40% of amount of heat is transported via oceans. So, in contrast to the atmosphere, the oceans are not limited, are not confined by land, by land masses. So the heat transport is more localized. It is in the specific regions. So winds have no limits, atmosphere has no limits, but oceans do, and this also has consequences to the whole system. So what makes the water move in general? There are primary and secondary forces that influence the currents to flow. First, primary forces are solar heating, winds, gravity, and so-called Coriolis force. Then there are secondary forces like temperature difference and salinity difference that we'll come to that later. So, first, solar heating. Heating by solar energy causes the water to expand. And this is why, for example, near the equator, the ocean water is about 8 centimeters higher in level than in, for example, middle latitudes. And this causes a slight gradient, and water tends to flow down this slope. And the flow is normally from east to west. Then there's influence of winds. Winds are blowing on the surface of the ocean and push the water to move. And there's a friction between the wind and the water surface that affects the movement of water body. And winds are responsible for the magnitude and direction of the ocean currents. And there is also the influences of gravity force. It tends, of course, to pull the water down and create gradient variation. And then there is a Coriolis force. And Coriolis force is caused by Earth rotating around its axis from west to east. And because of this, because Coriolis force exists, it causes the water to move to the right in the northern hemisphere and to the left in the southern hemisphere. So all those forces form and make water move and form the direction of their movement from those paths. And secondary forces are temperature difference and salinity difference. And water with high salinity in general is denser than water, which means it's heavier than water with low salinity. And in the same way, cold water is denser, that means heavier, we might say, than warm water. In the description of the lesson, and also in Polarpedia, in related term ocean currents, I placed a link to a game, which I find very interesting. It requires Flash to be installed, but I think it's really interesting. The game is to push a vessel, push a ship with use of currents. And there are two rules. There's cold water and dense water, and you have to use those forces to create ocean current and to make the vessel move. So I encourage you to do that. It's quite fun. These are the forces that make the water move. But let's come back to the primary force, the solar heating. How does it work? How those changes move matter, and how those changes in density move matter. This movement involves a process called convection, and it works for gases, but for liquids, for fluids as well. So to understand how convection works, let's imagine a room in a house, like this one shown in the picture. On one side there is a heater, and the heater is on, and on the opposite wall there is a window, and it's quite cold outside. So we have a cold winter day, the heat is on, air near the heater warms up. And what happens to hot air? It expands. When it expands, it becomes less dense and rises up. It reaches the ceiling and is pushed along by next air rising up. And the heated air starts to cool down the further it gets from the heater. And it speeds up when it hits the cold window, the cold air from the window. So the air cools and becomes, in contrast, more dense, sinks to the floor, and eventually completes this circuit of the room. And a circular convection current is set up. And this is what happens not only in a room with heater, also here when we have a hot land and cool sea, but the same thing, the same rule happens in liquids, in water as well. As for types of currents, there are many classifications we may use, but there are two main types of currents we can name. There are surface currents and deep water currents. So surface currents occur in the upper layer of the ocean, about 400 meters, and they involve only about 10% of all the water in the ocean. But the majority, 90%, is involved in deep water currents, so-called thermal currents, and of course they occur below 400 meters in this down layer of the ocean. Here is deep circulation, and here is surface circulation. So surface currents are mostly caused by the wind, because it creates friction and moves over the water. And the speed of surface currents is greater closer to the ocean surface, of course, and decreases at about 100 meters below the surface. And like I said, because surface currents travel all over long distances, the Coriolis force also plays a role in their movement and changes their direction and their pattern. And then there are deep ocean currents, which are driven by differences in the water's density, which is controlled by temperature and salinity. And temperature is thermal and salinity is haline. And this process is known as a very important process in the oceans, thermohaline circulation. Here we have thermohaline circulation. So in the Earth's polar regions, oceans water of course get very cold, and they're forming sea ice. But when water transforms from liquid to ice, as a consequence, the surrounding seawater gets saltier because the salt doesn't come into the ice. So it is left behind in the water. And as the seawater around the ice gets saltier, its density increases, which means it is getting heavier. It starts to sink. And surface water is pulled in to replace the sinking water, which in turn eventually becomes cold and salty enough to sink. And this initiates the deep ocean currents. Deep ocean currents, this second type, which is driving this whole system, which is called, in contrast, and this is another important term, global conveyor belt. This is the Great Ocean Global Conveyor Belt. It moves water around the globe and is very important to Earth balance. This is how it looks like, shown graphically, of course. So it's a global scale system, and it moves water around the globe. And why is it important? Because with this movement, it transports nutrients and also carbon dioxide. And how does it work? The ocean conveyor gets its start in the Norwegian Sea, about here, where the warm water from the Gulf Stream hits the atmosphere in the cold northern latitudes. And because of this clash with cold temperature, there's a loss of heat to the atmosphere, and the water, which was here, you can see it's red, it was warm, it gets cooler and denser. And what happens then? Of course, it's denser, it's sinking to the bottom of the ocean. So first, cold, salty, dense water sinks at the Earth's northern polar region. And then it heads south along the western Atlantic basin. Then the current is somehow recharged as it travels here along the coast of Antarctica, because it picks up more cold, salty, dense water from another polar but southern polar region. Then here, the main current splits into two sections, here and here. One is traveling northward into the Indian Ocean, and the other is heading up into the Western Pacific here. And then the two branches of the current here, the current of which has become warm. They're joined. They join again, and they look back around here, southward and westward. And this is a tropic region, so they are now warmed, and the now warmed surface water continue circulating around the globe, and eventually they return to the North Atlantic when the cycle is closed, when the cycle begins again. So they were warm, now they're colder, denser, sink, etc., etc. So the global conveyor belt moves slowly. It moves at much slower speeds, like few centimeters per second, than wind-driven surface currents, which have a speed of hundreds of centimeters per second. So it is a vital component of the global ocean nutrient and carbon dioxide cycle. Warm surface water here are depleted of nutrients and carbon dioxide, but they are not rich in nutrients and carbon dioxide, but they are enriched again as they travel through conveyor belt as both deep and bottom layers. So this is the base of the world's food chain, depending on those, not those warm waters, but those cool, nutrient-rich waters that support the growth of algae and seaweed. Let's see a short movie about thermohaline circulation. So this is basically how this is formed. As you can see, those arrows going down to the bottom. This is where the water gets saltier, denser, and colder, and turns around. This is the bottom of the ocean, of course. This image was created by NASA. So this is the beginning of the global conveyor belt. It goes down, it is recharged here around Antarctica. Then it was split into two branches, and the whole cycle begins again. So this is something I would like you to remember, how the global conveyor belt works. The rule is pretty simple, but the system is very, very important and quite complicated. So, what are gyres? Gyres are also a large system, an element of the system of circulating ocean currents, but there are those elements that are like rings, they're round, a ring-like system of ocean currents. And they are rotating, and if you look closely, you will see that here we have an equator, so here is the northern hemisphere, and here we have, of course, southern hemisphere. And in the northern hemisphere, they they're rotating like this, clockwise, here and here. And in contrast, in southern hemisphere, they are rotating like this, counterclockwise. It is because of Coriolis force I told you about before, because of this force driven by movement of Earth around its axis. And there are five main gyres: North Pacific, North Atlantic, South Pacific, South Atlantic, and Indian Ocean gyre. About Coriolis force, Coriolis effect, there's one interesting thing. We know it is caused by Earth rotation from west to east. To make it simple, when Earth rotates, different latitudes of the globe travel at different speeds. So, as a consequence, would you say there is where the Coriolis effect is the strongest? On the equator or on poles? What do you think? You're listening because there is a Kahoot quiz at the end. You can start preparing your smartphones. Once again, I will repeat that. If the Coriolis effect is caused by Earth rotating, and as a result, at different latitudes, Earth travels at different speeds, we might say, where is the Coriolis effect the strongest? On equator or on poles? On equator, there is no Coriolis effect, absolutely no Coriolis effect. As you can see here, those arrows are straight, and the maximum Coriolis effect is on poles. And I'll let you think about this. I repeat that once again. No Coriolis effect on equator, maximum Coriolis effect on poles. And I want you to think, why is that? Why is that the case? You can ask me later. So, what are the consequences? We're talking about those five big gyres. They have serious consequences because of pollution with plastic. Because gyres have a tendency to draw the pollution. When something is released in the coastal areas of the ocean, to the ocean, then the gyres is like sucking it in, it's throwing the pollution. As a result, there are so-called garbage patches or garbage islands formed. Mostly they are made of microbeads and plastic fibers, of all that we release into the ocean, directly or via rivers from the coast. And exactly the area of increased plastic particles is located in areas of gyres. So there are not only 5 gyres, there are 5 islands of garbage. And the most famous one is Great Pacific Garbage Patch. It is also described as the Pacific Trash Vortex. It's very, very big. It's 700,000 square kilometers big. So it's giant. So it's like more than two areas of Poland, for example. And it's not that there are like plastic elements floating. There are some plastic elements floating, but mostly it's microplastic particles that are very, very dangerous for marine life. Like you can see, it in parts it is like this. You can see like bags, trashes, maybe straws. But these are the consequences for the marine life. But not only. These elements are dangerous for marine animals, but also for the plankton, and they are polluted with those plastic elements. So why are the ocean currents, or is all this system, conveyor belt, thermohaline circulation, so important? Like I said, it's driving the movement of everything. For example, moving drifting organisms, that planktonic organisms that are not able to move themselves, like fish larvae, like plankton, like jellyfish, which allows the population to disperse, to reach new areas, and to increase their genetic diversity, for example. And this movement allows, for example, external fertilization of some fish, of some organisms that need fertilization, external fertilization, so brought by water. Of course, it brings oxygen and nutrients, and also CO2, carbon dioxide, because they're mixing. Without this, there would be areas with no nutrients, there would be areas with no oxygen and with no CO2, and the whole food chain would not be able to produce any food, any primary production. Also, it carries away pollutants and waste, which is good and not good, like you could see with those giant garbage patches. They are gyres, those round ring-like currents suck in some particles. So what we put in the ocean is brought further by the oceans. And also the transport of heat is influencing weather and climate. So just in short, for ecosystems, availability of nutrients is very important, transport of eggs and larvae, and distribution of the marine life. Like, for example, it is very important for the dispersal of many life forms. Here you can see the example of the life cycle of a fish, European eel. You can see it here, this long fish that needs ocean currents to breed, to produce offspring, because it's carried away by ocean currents from one environment to another. Without it, it would not be possible. As a consequence, it is very important for fishery, because rich fishery areas occur where different currents meet, because there is a mixing in ocean fronts, and the feeding grounds are fertile. There's abundance of food. So this is why the polar regions are so rich. Northern seas are so rich, different type of fish, and are a great area for fishery. It also has a consequence in transport, because their water currents are one of the most important factors, affecting not only the distribution of pelagic larvae, like I said, but also having impact on human transport. In the past, the knowledge of surface ocean currents was essential in reducing costs of shipping, or even allowing it to move. Marine transport was even more important than today, especially in the wind-powered sailing ship era. The knowledge of ocean currents was essential. An example of this is Angola current. For a long time, it prevented Portuguese sailors from reaching India because they weren't able to cross it. They didn't know how it moved and they weren't able to cross it. In recent times, around the world, sailing competitors make good use of surface currents because they want to build speed just to break some records in their championship. Today, ocean currents are also gaining significance as a possible form of alternative energy. We keep looking for clean, green energy. And because water is dense, it carries an enormous amount of energy. It could possibly be captured and converted into a usable form through water turbines. For now, there is a use of waves, but the use of currents is only an experimental technology. It is being tested by United States, Japan, China, and some EU countries too. So for now, it's just an experiment, but waves and tides are already used. So if we're talking about currents, we have to know at least some of the names of the most famous currents. And these are 17 major surface ocean currents. Remember, there are surface ocean currents and deep currents. And they vary in size, importance, strength, and like I said, here are the best known, like Labrador Current, California Current, Alaska Current, Equatorial Counter Current. But let's focus for a minute on this first one. Okay, here are their names with their distribution too. The first one and the most well-known one, Gulf Stream. One of the strongest ocean currents in the world. It is driven by both surface wind patterns and differences in water density. Why is it so important? It is an Atlantic current and it influences the climate of the east coast of North America, from Florida to Newfoundland, and the west coast of Europe here. It is making this climate more warmer in general, more mild. The image on the left shows surface temperature in the western North Atlantic. So the North American landmass here is black and dark blue, cold, and the Gulf Stream is red. So here is the Gulf Stream. Here's this giant mass of warm water. And recent observations show that since 1950s, there's a decrease in the flow of Gulf Stream. And it is because of climate change. Why is that? It is driven by, it is a warm current here, this is the Gulf Stream, but it's driven by movement of cold water. And when this source of cold, dense water is decreasing, the Gulf Stream is decreasing as well. And the IPCC believes that it is very likely that this current, Gulf Stream, will slow down during the 21st century, and about 25%, some models say. This means that it will no longer make climate in here and in here warmer. So these are some basic data about the Gulf Stream. It is warm, it is 100 kilometers wide, and this deep, up to 1.2 kilometers deep. So about this climate change, when there is a disruption of the system, like of a global conveyor belt, the Gulf Stream is a good example. The climate is no longer modified by the ocean currents. And of course, because global conveyor belt is strong, but it is very easily disrupted process. And rising the sea temperatures, increased fresh water from melting ice from polar regions are changing the ocean conveyor. Okay, if global warming results in increased rainfall, for example, in the North Atlantic, and there's a lot of melting of glaciers and sea ice, there is an influx of warm, fresh water onto the sea surface, and it is blocking the formation of sea ice. It is disrupting the sinking of cold, salty water, so this whole process is disrupted. Other consequences are, of course, disruptions of plankton cycles, food webs, and fishery, which is a serious economic consequence too, not only for ecosystems, and El Niño effect too, which tends to cause catastrophic weather events.